Hey guys, it's Mr. Wolf. I'm going to be going over a couple examples from your lecture notes on how to tackle some of these problems. But before I go to the actual word problems first, I'm just going to review over basically the fill in the blanks here. Also, if you're watching this video, make sure that you've watched the Target 3 sheet as I go through that Target 3 sheet video first, and then watch this one. So this is on page 24 of your packet. So when two objects interact, Newton's third law tells us that they exert equal forces on each other. The time of contact is also the same for both interacting objects. Because of this, we know that the impulse the objects exert on each other will also be equal in magnitude and opposite in direction. This means that when we add the impulse vectors together, we get a net impulse of 0. They basically cancel each other out. So no net impulse means no change in momentum. Right? And the law of conservation of momentum going along with this here states that in the absence of an external force, the momentum of a system remains unchanged. Momentum lost by one object is just simply gained by another. The total amount of momentum will stay constant. So I went over this in the Target 3 sheet, but basically the total momentum before is going to equal the total momentum of our system afterwards. All right, so let's look at some equations here. All right, so right here, this is going to be an example of an elastic equation, where basically our objects are going to be bouncing, and we know it from this equation. Everything's going to be separated right here. And so right here, this is referring to the momentum of our object right here. M2V2 is referring to the momentum of our object here. And then that's going to be equal to those objects afterwards. All right, so there's multiple ways that we could set up this equation. We could do it through the tables, what you guys were working on earlier before, and through the equations. I'm going to set up this problem with a table first. Unfortunately, they don't give it to us. But kind of make it where we have mass here, velocity here, momentum here, separated. This will be before, this will be after. We have mass, velocity, and momentum here, and that'll be after. And then finally, we're going to be looking at this for the gray ball right here and the white ball right here. Finally, what we're going to want is this total momentum once we add these up. So I'm going to put total here. All right. So let's look at the mass. The mass is pretty easier because it's not going to be changing. For the gray ball, we have 8 grams, but it says make sure that we convert to kilograms. It's going to be 0.008 kilograms. It's going to be the same afterwards. Our mass isn't going to change. And then the white ball is 0.005 kilograms. Right? It's traveling, initially the gray balls are traveling with a velocity of 3 meters per second. I'm not going to put in my units here just so it just doesn't get too messy. I'm just going to be putting in the numbers. But our mass is going to be in kilograms. Our velocity is going to be in meters per second. Our momentum is going to be in kilogram meters per second. All right, and then the momentum of the white ball is going to be -7 meters per second. All right, so what I'll do is when I multiply these together, I'll get my momentum of the gray ball beforehand. And that's going to be 0.024 kilogram meters per second. When I multiply my mass and velocity here for the white ball, I'm going to get a momentum of 0.035. This will give me a total momentum of -0.011 kilogram meters per second. All right, so before we go on, we know that the total momentum here has to be 0.011 by the law of conservation of momentum. I can immediately fill in this box once I have this one. All right, and so keep in mind what this problem is looking for is what is the velocity of the white ball afterwards. All right, so that's kind of our question mark right here for now. If we look afterwards, they give us a velocity of 2 meters per second, -2 meters per second. And that'll give us a momentum of -0.16 kilogram meters per second. All right, so here's what we have. We don't know. We don't have this momentum as of now, and we don't have this velocity. We need to find this velocity. Now, one thing we do know is the total momentum of our system, and we have one of those momentums that's going to be part of our system. So what we could do is we could set this up as a simple algebra problem where we know that the momentum of object 1 and object 2 is going to add up to equal negative 0.011. And so we could actually find this momentum right here, right, solving for x, and we're going to get positive 0.005 kilogram meters per second. And so now we have the momentum, we have our mass. Basically what we have is P equals mv. We have our momentum, and we have our mass. All we need to do is solve for velocity. In this case, it's pretty easy. Our velocity is going to be 1 meter per second. It's going to be what we're looking for. So what is the velocity of the white ball? 1 meter per second. So we've solved this problem going about it this way. All right, and we're going to look at a similar problem, but we're going to go about it focusing on this equation more. All right, they're just two different approaches. Okay. And so here we have basically a bowling ball colliding with a pin. It hits the pin and the ball goes flying. In this case, it's asking, what is the mass of our pin? All right, and so what we'll do is this is going to be an elastic collision just because these objects are not sticking together. They'll still bounce off each other even though they're going to be still going in a similar direction. All right. So if it's an elastic equation, what we're going to be using is our elastic equation right here. This is also in the target 3 sheet. It tells you what equation to use for an elastic collision. All right, so that's going to be m1 v1, which is the momentum of this object, plus m2 v2, which is going to be the momentum of this object. It's going to be equal to the momentum of the objects, the sum of the objects afterwards. So m1 v1 plus m2 v2. All right. So the mass of our first object of the bowling ball is going to be 4. We're going to multiply that times its velocity, plus, and we don't know the mass, remember we're looking for that, right? Multiplied by the velocity. Now it's standing still, so we know it's 0. Basically, if we have 0 in the system, our total momentum is going to be 0, so we don't need to worry about this right here. That's why I crossed it out. And then finally, our momentum afterwards, we're still having a 4 kilogram bowling ball. Its new velocity, it's decreased to 4.5 meters per second. And finally, we're going to be looking for that mass with a new velocity of 3.2 meters per second. All right, so now we've set up our equation. We just have one variable here, the mass that we need to solve for. So we just need to break this down and solve it algebraically. To m. All right, and when we do the math on this, we're going to get a mass of 0.625 kilograms for our pin. All right. So for the check for understanding number 6, what I want you guys to do is, I'll check this for homework tomorrow, is work on this on your own. But I expect it to be completed by tomorrow. But and then we'll go over this as well tomorrow. All right, so let's go on to the next one. This is going to be the last problem that I work through with you guys, and I'm going to go about it not using the chart but using this equation again. All right, and so here we have a new situation. This is going to be for sticky situations. So think if they're sticking together, this is going to be an inelastic collision, right? Where once they collide, they stick together going this way. So we have two train cars colliding, sticking together going this way. And it's asking is, what's the velocity of the two attached cars? So these two cars together once they collide. And so we're going to be using this equation, which is very similar to the other one. The only difference is and I don't like how they wrote it here. What I would rather have is, for our after, is that our mass 1 plus mass 2, because we could treat these masses as the same object, and then the velocity right next to it right there. And so I'll even write this out again. All right, so the mass of our first train car is 500 kilograms. I'm going to multiply that by its velocity, 7.5, plus the momentum of our train car right here, which is basically at rest. So even though it's 600 kilograms, we're going to be multiplying that by 0. We can basically not worry about that for now. All right. And then the mass of our cars together is basically just adding the masses up, 500 plus 600, and we're going to be solving for the velocity right here. So here we've set up our equation. We have our one variable that we're looking for. So we're just going to do the math on this. Right, and we're going to get a velocity of 3.409 meters per second. It's going to be positive going to the right, which makes sense, as our object is traveling to the right. Right. So again, just to kind of go over, we have an inelastic collision where they're colliding, and an elastic where they're bouncing, and everything's basically kind of separated here. What we're doing here is, since they are sticking together, we could treat the masses as one object right here. So that's why it's m1 plus m2 here. All right. So for this last problem, this is going to be an example of recoil. So basically, we're going to have an object, our cannon and our cannonball within our object. So what we could do is, and I'll help you guys set up this equation. Since we could treat these two masses as the same object in our before collision, it'll be m1 plus m2, and then its velocity. All right, it's going to be equal to, and then since once that gunpowder explodes, the cannonball is going to be traveling this way, and it's going to exert a force on the cannon, so it's going to be traveling this way as well. We're going to have to separate these. Right, so this will be the momentum of our cannon, and this will be the momentum of our cannonball. Right, so this is the equation we're going to use for recoil. So I'll have you guys work on this, try to solve this. We'll be going over it in class tomorrow. And then what I also want you guys to do is, we'll discuss this in class tomorrow, but I want you guys to write an answer to this right here. Is there such thing as a conservation of velocity? And so I would also look at some of the example problems here to help you solve that, and also look at that target 3 sheet that you created for this. So I'll be checking this page tomorrow, along with that target 3 sheet completed. I'll see you guys tomorrow.